Here we are again. Let me set the timer. Alright, I was trying to name the moving with a constant velocity equilibrium and started to spell it wrong. Dynamic equilibrium. So this is static rotational equilibrium. This is dynamic rotational equilibrium. A couple definitions that parallel what we learned previously. So, again, if you need to pause, do so. Alright, and the very last thing is we took a stick like that, and it's laying on the ground, and it's a still stick, still stick, still stick, still stick. The still stick is in static equilibrium. It's not moving, it's not rotating. In rotational, it's not moving this way in translational, so therefore it's in equilibrium. Today we're going to look at it as rotational static equilibrium. It's not spinning. But if I take that stick and I put it on a fulcrum, the fulcrum is a balancing point. Do you see that now this stick can move in a circular way? This point can move this way, and this point can move that way, creating circular motion, or the opposite. This point can go this way, and this point can go this way. So there we have an example of rotational movement with a stick on a fulcrum. And when we were young, we called it a seesaw. You don't see too many of those anymore. They were kind of nasty things. You get really hurt on those. We did a problem with this, and we recalled that sometimes there's a person of one weight on a seesaw, and then a person of a different weight on the seesaw. So in order to put those in static equilibrium, where it's actually still, we usually have noticed that the larger person had to sit in closer, or was it the closer to the fulcrum for that to work. And we're going to try to figure out exactly where these people have to sit so they are balanced. To do that, let's set up a problem. This person weighs 201 newtons and is 1.3 meters from the fulcrum. This person is an unknown weight and sits 1 meter from the fulcrum. And the question is, if this is in static equilibrium, how much is the unknown weight of this person? To do that, we used to work with the sum of the forces is ma. But today, our forces are called torques. So I'm going to change Newton's law. It still holds for torques. The sum of the torques is ma. Let me see if that shows up well. All right, pretty good. Now, how many torques are they, and what are their signs? Well, the torques are, again, over here, torque equals force perpendicular times r, a distance from the center. So here, how many of those pairs, force times r, do we see in this picture? Here this man, or child, has created a force. His weight has created a force of 201 newtons. And the r, his distance from the center, is 1.3. So we found 1. So I'll go torque 1. So call him torque 1, that his weight causes. His torque will cause the seesaw, like if no one was on here, his torque would cause a rotation this way. We have defined that as counterclockwise or a negative torque. take this guy away, if this was the only person here, he would create a torque this way. That's called clockwise, and we named that as positive. That's arbitrary, but physicists have decided that clockwise torques are positive and counterclockwise torques are negative. So with that, we have a torque created by this one and a torque created by this one equals ma. So I only see two torques in this problem right here. Torque 1 and torque 2. All right, what is the torque? Well, it's force, 201, times distance, that's the r. We use r because it's really a big circle and the distance from the center is like the radius, and it is 1.3. Now we're up to the plus sign. Torque 2 is the weight we don't know. His distance or radius is 1. Now we're up to the mass and the acceleration. Because I could calculate his mass, but I know that he's there in static equilibrium, so the acceleration is 0. So all I have to do is solve that equation for W right here. So I have W equals, move the 201 times 1.3. Oh, I'm sorry. This is a negative torque. So torque 1 had to come with a negative sign. So multiply 201 times 1.3 and move it over to the other side. And the weight comes up to be 261 newtons. So that's all we did today. And our assignment is OYO 6.6 and 6.7 that reflects this material. The reading just before that is optional. If you had trouble understanding this material or not able to do these OYOs when you look at them, go ahead and read it. It is not required, but it will help you if you had trouble following the lecture. So OYO 6.6 and 6.7 are due tomorrow in class on Thursday. And that's all there is to that. I'm sorry that you guys were out today. So let's see, it was Aaron, Alex. Was that all? 1, 2, 3, 4, 5, 6, 7. Yeah, I think that's all. So I hope that you guys are feeling better and can join us tomorrow. And I will send you a quick email to let you know that this video is available for your enjoyment. All right, I hope you're up to watching it. If not, as soon as you are, take a glance at it and see what you missed in class. We missed you. Bye.